Hello, everybody, and welcome to this talk organized by QtDay, a series of events dedicated to the Qt framework. We're very happy you could join us today. QtDay is organized by Develer, a company that develops hardware and software with industrial applications, with great focus on emerging and open source technologies. It is also the first company in Italy to receive Qt Specialist certification for its staff. At Develer, we strongly believe in supporting training and collaboration, and because of this, we regularly organize technology events such as conferences, workshops, and courses dedicated to state-of-the-art technologies like Qt. In fact, we have an online course coming up in October. Registration is already open for our Qt Quick Pro course, and we have an early bird offer. If you register before the 31st of August, you will get a substantial discount. You can see more info at the link up here. The course will be held in the Italian language, so only our Italian speakers in our audience will be able to attend. At the end of the talk, we will have a Q&A session, and we will have a dedicated Q&A chat, different from the regular chat that you have during the event. So we would kindly ask you to wait and write your questions in this dedicated Q&A chat. Today's speaker is Burkhard Stubert, who will share his insights in a talk about how to get the architecture of Qt embedded systems right. Burkhard is a consultant, and he helps companies succeed with Qt embedded systems. Among his major products, we find the information and entertainment system for a US car manufacturer, and the driver terminal for a sugar beet harvester called ROPA, and the driver terminal for a forage harvester of a brand called Krone, so industrial applications. So we welcome Burkhard, and we are very happy to have you with us today, and with this talk about the architecture of the Qt framework. Hello, how are you?
Hello.
Very glad to have you here. Okay. So I will leave you in his capable hands, and we will meet again for the Q&A session. Enjoy the talk.
Thank you very much, Laura, for the lovely welcome. And welcome to all of you to my talk about how to get the architecture of Qt embedded systems right. Last year at QtDay, I hoped that we would meet in person this year, but unfortunately, well, it's still not possible. So my hope is for next year to come to Florence and to enjoy the lovely atmosphere at the Develer events and meet you in person again. So let's hope that that works out. And by the way, my wife needs new shoes. And with her size 35, she only gets them in Italy, not in Germany. We have larger feet, obviously, here. So let me start my presentation. Click on. So you should now see my screen. Today, I'll show you how to create the architecture of a harvester terminal. And you will now wonder, why harvester terminal? And how applicable is what I tell you for other Qt embedded systems? Well, the answer to the first question is pretty simple. I've built two harvester terminals, as you learned in the introduction. So a forage harvester and a sugar beet harvester. And I've built a couple of infotainment systems for cars, for e-bikes, for planes. And that already covers quite a wide range of devices. So we have consumer devices, we have industrial devices. The second question needs a little bit of explanation. How applicable is it? When I build an architecture, I look at the ecosystem in which the Qt embedded system works. So I look at with which other systems my system interacts. And you see here on the photos, you see a lot of questions you should pose when you build an architecture. So already the pictures give you some ideas. So what are the operating conditions, for example? You see, well, it's definitely it has to work at nighttime, at daytime. You see here, it's obviously on the field. It can be, it's in summer, but it can also be in December. You see here, it's picking up grass. Here, it's on the left, it's cutting maize, so it's two operating modes. You always see, you see the driver of the harvester, you see a tractor with the driver to transport away the harvested goods. So that's already a lot of questions you can pose here. And if you look at the terminal itself on the right-hand side, well, you have certainly questions like, what SoC, system on chip or SoC, should I use? Is it a single GUI application? Is it a multiple GUI application with a window manager? Well, does it support multi-touch? Typically it does these days. Or is there keyboard input as well, like with the joystick here, or a rotary encoder, which is hidden back here so you can't see it? And what is actually in 2012 that looked totally different than, or the answers to the questions would be totally different than in 2021. So how does the right architecture look? So I've been throwing around things like right architecture and successful architecture, and you might be, hang on, I have to backpedal a little bit. I still have to answer the second question. So the thing is, the questions, what I found is the questions are the same for different, or nearly the same for different embedded systems. The answers are the answers are different. The questions are nearly the same. The answers are different, and the priority of the answers are different. So that's why what I tell you here about harvester terminals is also pretty much applicable to other embedded systems. So now, I've thrown around terms like right and successful architecture in the original title and in my new title. And what you see here on this slide is basically my learning process over the last 25 years. So yeah, that's how old I am actually. I started with, well, probably with the famous big ball of mud architecture or spaghetti architecture. And then I learned a little bit about design patterns, so model view controller, and or publisher, subscriber, and I started adding these things to the architecture of my systems. Some of the ideas were good, some were totally bad. So I slowly developed a feeling for good architectures. Say a three-layer architecture, so the model view and then a data consumer, a data producer. So by learning and by reading a lot, so I figured out what a good architecture might look like. And it's a technically sound architecture. So even a microservices architecture would be technically sound. Whether it's the right architecture for a Qt embedded system, I doubt. So it's probably far too complicated and it's a little bit off topic. So the right architecture must meet the stakeholder needs. And so that's why, well, microservice, that's more an enterprise or cloud architecture. So the right architecture could be, say, a three-layer architecture. And actually, the three-layer architecture served me pretty well. It might not have been the 100% perfect solution, but it always was a good solution. And I have some systems out there in the field for now nearly 20 years and some others for 10 years. So I would say these architectures were successful. So they delivered value. My customers didn't have to throw my stuff away and redo it, but they could extend it, adapt it, and work with it over 5 and 10 years, and some even for 15 years and longer. So a successful architecture must deliver value. So the customer or your employer invests a lot of money into the product, into the architecture, into your development efforts, and they want to get back some money. And that's the value they need. So a successful architecture may not be the perfect architecture in terms of being right, but it's an architecture with which your customer or employer can make money. So, and by now, I think it was somewhere this year when, no, it was 1 or 2 years back when I learned about the hexagonal architecture, or the ports and adapters architecture. And that's actually the architecture where I would say, yeah, that should be the de facto standard architecture. And I'll show you why. And it makes a lot of sense. So you can save a lot of time now, and you do not have to go through my process, through my learning process. But you may want to start with the ports and adapters architecture or hexagonal architecture, and use that as your starting point, adapt it, extend it as needed. And you'll see why it's probably a good starting point. The ports and adapter architecture is the base for all our GUI applications, and we may have one or multiple GUI applications. It was created about 20 years ago by Alistair Cockburn, and it's, well, more for enterprise systems, but I think it fits pretty well for embedded systems, especially embedded Linux systems. So the idea for this architecture comes from hardware ports and adapters. So I'm sitting in front of a Mac, and while you all know the joke about Macs, you need to buy about 5 very expensive adapters to work with it. Well, I have one connected here, USB-C. It adapts to USB-A, to HDMI, and to power. So and that is a pretty typical thing. PCs nowadays come with half a dozen or so USB ports. They do not provide serial ports anymore, or CAN ports or so. They just have USB ports, and you buy the adapters you need. So you will buy a CAN adapter for some money, and a serial adapter, even LAN and wireless LAN adapters, and so on. And you can do that because USB ports are standardized. So they are standardized on an electrical, on a mechanical, and on a logical level, and higher layers. So that's why that works. So different companies can build different adapters, which is good. And now we transfer this idea from the USB adapters into software, and that's what we get now. So at the core of the ports and adapters architecture is the business logic. And the business logic is basically what the PC is for in our hardware analogy. And the business logic now provides, here it's 4 ports. So 1 port with the models to the GUI, of course a port to the machine for machine communication, then probably a logging API which goes to the cloud and also stores things in a local database. And you typically have a customer database to do all the accounting for your customers, while someone has to pay for the harvester cutting maize or digging out sugar beets. So that needs to be accounted for and invoiced for. So you have these ports or interfaces, and a port is an interface between the business logic on the inside, the red thingy, and the adapters on the outside. And you typically will have something like 4 to 6 adapters, not necessarily more. An adapter uses or implements a port or interface. So the GUI typically just uses the models you provide through the model API. The machine in a port implements or the machine adapter, sorry, the other way around. The machine adapter implements the machine port. So to allow your terminal to communicate with the machine. And you see here already, you have one API can have multiple machines, can have multiple adapters. So the machine API, for example, has a machine, so which does the real communication. It has a simulator, so you can work with a simulated machine during development, and it has a mock adapter for testing purposes. The important thing, and that's the one takeaway, or the most important takeaway here, is code from inside, from the business logic, must not leak into the adapters, and code from the adapters must not leak into the business logic. That is an absolute no-go. So the business logic, for example, must not know that the machine adapter down here uses, say, CAN bus, for example, which is part of Qt serial bus. Why? Because well, maybe in 3 years you decide that you want to throw away CAN bus, it doesn't have enough bandwidth, and you use Ethernet instead because, well, you have your ECUs, your electronic control units in your harvester are connected to Ethernet anyway. So why have CAN and Ethernet? And you can do that change, and it only affects your adapter here. The business logic doesn't even notice whether you use CAN or Ethernet or Bluetooth or whatever you want to use down there. And the same goes for the other adapters. So that's the important idea. And the ports can typically, they are connected with each other through signal and slot connections, but we'll see that on the next slide. So we can now unfold the adapter business logic adapter path into the very well-known 3-layer architecture. So I guess you are all familiar with that, or you should. So you have the view with the GUI on the top. Then you have the models or the business logic, and somewhere and down there, the 3rd layer is typically a data consumer or data producer. So we have here. I show 4 instances of the 3-layer architecture, nicely unfolded from our hexagon. So the first is probably our first version of our product, and then, as I already hinted at, well, in 3 years you replace Ethernet, CAN with Ethernet, and this happens only down here in the 3rd layer. The 2nd and the 1st layer won't even notice. Fantastic. You can take that a step further. During development, you will use a simulator. It's actually also a cool way to find bugs in reality. So you record a CAN trace on your harvester, and then you replay it through the simulator. So it's a fantastic way to find tricky bugs. So the simulator actually, it's another adapter. It talks via inter-process communication with your application. So it's yet another adapter. And the final one is now for testing, for system tests, for example, or even for unit tests. So you replace the GUI by a test. The business logic is the same. It never changes. and you replace the machine adapter by a mock, so that you have more control over which data is produced or consumed by the machine. So the nice thing is, or the advantages are pretty much the same as with hardware adapters. Different people and teams can work on different parts in parallel. And what should be clear by the explanations by now is you have a very high modularity, testability, maintainability, and modifiability. And it's only the adapters, the implementations which change, the interfaces always stay the same. Okay, on a harvester, the terminal talks over CAN with the machine. So you actually have two different embedded systems. On a TV now, well, there is no machine, wouldn't fit in the TV, but you have the TV tuner would take the role of the machine. So your application talks to the TV tuner, say a satellite tuner, DVB-S tuner, over IPC. And the app and the machine are on the same embedded system. So although the TV doesn't have a machine, the mechanism for communication with the TV tuner is the same as on the harvester. So you can apply the lessons from the harvester again on the TV tuner. Good. So how does, say, the CAN adapter look like? So how does the structure in the CAN adapter look like? You see at the top, you see the business logic, then you have the machine API or port, then you have the CAN adapter, which uses QtCAN bus, of course, to read from the real CAN buses. So we have two of them, or to write to the CAN buses. The important thing is, and you will hear that a couple of more times, the important thing is that the business logic must not know that the adapter uses CAN bus at all. It just must not know that. That makes your application very flexible. So just flip it out against an Ethernet adapter and your application will still work. So the business logic only knows about digital twins of your electronic control units, of your ECUs. So for each ECU, there is a digital twin in the machine API. So there is a body twin for the body. There is probably a steering twin for the steering, a climate twin for the climate ECU, and so on. So you get the picture. The body twin has multiple quantity properties. They are typically implemented as Qt properties. A quantity is something like 6.73 kilometers per hour or 23.2 millimeters. So it's always a value plus a unit. That's a quantity. The twins also have a list or provide a list of errors. So the errors that happen in the respective ECU. So then the port, so the machine API, can exchange quantities and errors with other ports. So obviously something like the vehicle speed will be forwarded to the HMI. So through the model API to the HMI. And it will, so errors or relevant quantities will also be forwarded to the logging API and then to the cloud, or the errors will be also logged in a database to check them later. What went wrong? The adapter has a couple of responsibilities. So one, or the obvious one, is to decode and encode CAN bus frames. So a QCAN bus frame is, in the end, it's just a sequence of 8 bytes. And then it can contain, one 8-byte sequence can contain multiple quantities, multiple errors. And they are extracted out of the frame and then become quantities and error objects. So you actually lift the very low, or the 8-byte sequence is very low level, has a very low abstraction level, probably nearly as low as it can get. But on the machine API level, you work with quantity and error objects. So you have a much higher abstraction level. And this is actually a sign of a good interface. You need an interface must provide a good lifting of your abstraction level. So your abstraction level must be a lot higher. Another responsibility, and a pretty important one, is that the adapter must avoid GUI freezes and stuttering. The most important thing to achieve that is that the CAN processing must not be done in the main GUI thread. So just keep in mind that the terminal sees something like 1,200 CAN messages per second. So if they just flood into the GUI, the GUI will freeze and crash. So what you do is you do the CAN processing in extra threads. So you move that out of the main thread, and you have a processing thread for each CAN bus you have. So you have 2 here, and then you connect or you transport the CAN messages or the quantities and errors to the machine API through signal and slot connections. And as the CAN processing is done in one thread and the machine API runs in the main GUI thread, you have asynchronous signal slot connections. So this is the situation if you do the CAN processing in the same process as the application runs. That is a good approach if you have a single GUI application. If you have multiple GUI applications, you move your CAN processing into a separate process. And that process doesn't do anything else but decoding, encoding CAN frames and creating quantities and errors out of that. It communicates with the multiple applications through inter-process communication, like QRemote objects or dbus, for example. So and now, your CAN processing and your applications run in different processes. You can take that even a step further and offload the CAN processing onto, say, a microcontroller on your SoC, on your SoC. So modern SoCs, like the IMX8, for example, they come with 4 application processors, so Cortex-A53s, and they come with 1 Cortex-M4. And why let the Cortex-M4 sit there and twiddling its thumbs? So you can use it to do the CAN processing, and then it communicates with the applications through something called RPMSG, which is in the end just some shared memory between the microcontroller core and the microprocessor cores. So the lesson here, or what you should take from here, is it doesn't matter where the CAN adapters run. If they run in the same process, if they run in their own process, or if they run on their own microcontroller. The machine API will be always the same, no matter where CAN processing takes place. And Yeah, so that's, I think, the umpteenth repetition of this, but it's important. It's why this architecture works. In the next section, we'll answer two questions. Does our system need a window manager? And which window manager is best suited for our system? Okay. If you have a system with a single GUI application, you do not need a window manager, or what you need is a very simple, simplistic window manager. If your SOC does not have a GPU, you will resort to software rendering directly on the Linux frame buffer. So you have no graphics acceleration, you must use software rendering. So your CPU has to do the rendering. Most SOCs these days, especially the ones you would use in a harvester, in an application like that, they have a GPU and provide OpenGL acceleration. And then you use EGLFS. So this is a so-called Qt platform plugin, and it's the simplest one, maybe as simple as Linux frame buffer, but with graphics acceleration. So EGLFS renders a single Qt application on a single full screen window. Full stop. Single application, single window. You can't have multiple windows and switch between them. That doesn't work. These days, you can actually have, say, dialogues, which are top level or often top level windows, and these dialogues are then rendered into the first top level window, which is your single full screen window. So that works by now. 5 years ago, that wasn't possible, but even EGLFS develops nicely. So it's a little bit restricted, EGLFS, but it's still good enough for many Qt embedded systems. So actually, I've built most of my systems with just EGLFS. So the terminal for the Krone forage harvester and the terminal for the ROPA sugar beet harvester, they both use EGLFS. The first one has moved to Wayland by now, to a window manager. The second one will probably do that. So the writing is on the wall. But it's a perfectly good starting point for single application systems. So when should you use a window manager? Well, you should definitely use one if your system is naturally divided into multiple applications. Think of an infotainment system in a car where you have a radio application, a media player, a navigation application, a settings application, a climate application, and you have a couple of third-party applications, say parking search a free parking place application. Using multiple applications with window manager has also a good effect on reliability. If one application crashes, say a less important application crashes, it doesn't crash the complete system. So if you have a single application system and you have a bug, say somewhere down in some settings which you use once in 5 years, and that's hit, well, goodbye, your complete system is down. You don't want that. If you have multiple applications, you will typically have multiple teams or multiple people who take care of each application. Actually, it's interesting that multiple applications may sneak in from behind. So both harvester makers with whom I worked had the need for remote support and diagnostics. So they want to avoid that they have to send a technician half around the world and for a lot of money and screw in something and then fly back again. So a very simple way to solve that is to put a VNC server on your system and mirror your display to the PC in some office half around the world. So it works nicely. Or you also want the other way around. You have a VNC client running on your system to mirror the applications running on your smartphone. So that's what Apple CarPlay and Android Auto do, although they don't call it VNC, but well, that's marketing. It's the same thing lying underneath. When should you not use a window manager? Well, if your SOC doesn't have a GPU, it might be hard pressed to cope with the demands of a window manager. Well, if your BSP, your board support package, lacks Wayland support, well, you might not use a window manager. So that was the case with the ROPA sugar beet harvester some 5 years ago. Wayland was around and other BSP supported it, but the BSP we had didn't do it. So, well, we used EGLFS instead. So the question you have to ask yourself is a window manager always provides extra complexity? And so the question is it worth to spend this extra effort for this complexity, or is it needless complexity? If you say yes, it's needless, then don't do it. So on a harvester terminal and probably on all embedded systems or most embedded systems, you do not want a desktop window manager like, say, X11. It places the windows wherever it sees fit, but it definitely doesn't place the window where you want it to be placed. So the typical requirements, say, for a harvester are, you want to see the main window all the time. So the main window contains the information, the relevant for harvesting. And the driver always needs to look to have that in at least in his left eye, if not in both eyes. So that's paramount. Sometimes the driver needs some extra information, so that when he clicks on one of the application buttons here, down here, and then say switches on the camera for the view of the turbine, which cleans the sugar beets, for example. It's still important, it's a split view. The main window is still visible, probably in an easier, simpler representation, because you have only half the space available, but it's still there, so the driver can still see the important information. Obviously, the window manager must be able to handle touch. It must also be able to handle hotkeys from like from a joystick or from a rotary encoder. So think BMW iDrive, something like that. The cars all have that, and it's actually with a rotary encoder, you do not have to look at a screen. You can do that blindly. Touch screens are distractive because you have to look where you touch. So I already discarded X11. Well, the problem is you can't. It's nearly impossible to place windows at the correct region of your screen. The best option here is a Wayland compositor, and you have two Wayland compositor options, or you have two options here. You can use the QML Wayland compositor, and that gives you the full power of a QML program. You can animate the windows. Now it's the windows of the applications, like you are used to from QML. You can play graphical effects. So you could place your windows on your windows on the different sides of a cube, for example, and then rotate the cube. So some nice 3D animations. That's all possible with the QML Wayland compositor. So it's fully customizable. You have the full control what to do. The licensing is a bit problematic. In Qt or Qt 5.14 actually dropped LGPL licensing. So you have to find a workaround. You can work with the Wayland compositor from 5.13, which is under LGPL still, or do some other workarounds. The other option is Western. Western is a default Wayland compositor, and many BSPs actually build Western and start Qt application when you power on your board. So I've just seen that on the last two boards I've been working on. It's not as fully customizable as the Wayland compositor, but it's freely configurable, so you can tell Western where to place a window. It's under MIT license, so you can basically do with it whatever you want. And you have, for example, an example implementation with the Geneva Layer Manager, which is a window manager for infotainment systems in cars. The choice of the operating system is simple. Use Linux. What else? So, okay, joking aside, let me be a bit more diligent and tell you why. Linux, if your embedded system has an operating system, then Linux is the most used operating system for these systems. It doesn't have any license fees. The BSPs, so the board support packages, are always available for embedded Linux. You have many free high-quality tools like compiler, a debugger, static analysis tools, Qt Curator, all of the Qt tools, the Qt libraries, for example, and a lot more. So you don't have to pay a lot of money to get these tools. It fits many, if not most, use cases for embedded systems. And it's known by many developers. So most of us have probably at least dabbled around with some desktop Linux. Maybe you are like me, so I've been developing all my professional life on Linux. So I don't even know what Windows is. But Android, well, it is based on Linux, obviously. You see it less in industrial applications. You see it growing in consumer products like TVs, set-top boxes, even cars, infotainment systems in cars. Volvo, for example, uses Android by now. The reason, I think, is that it has a huge app ecosystem, and you can run applications, typically games, on your TV or on your set-top box or on the rear seat entertainment system of your car. Hopefully not on the instrument cluster for the driver. The other option, the lesser use option, is a real-time operating system, and you find these used in special contexts for special application cases like safety critical applications or real-time applications. So think of medical devices. They are safety criticals. Lives depend on it. Or even the ECUs in harvesters, in tractors, in cars, they are safety critical. Well, the knives of a cutting drum of a forage harvester can easily kill you or cut off your leg. So that is their standard application scenario. The bigger ones like QNX, Integrity VxWorks, they have license fees attached. They're not, they're pretty high actually. But you also have some free real-time operating systems like FreeRTOS or Zephyr, which is the Linux-like one. And these are very well suited for the Cortex-M core on your hybrid SoC, like an IMX8. And they save you a lot of development efforts. For example, you do not have to write a CAN driver. FreeRTOS provides one, or Zephyr provides one. And without an RTOS, if you do bare metal, well, you may have to write that yourself. I won't say much about Windows. It's on life support, so to say. Well, I haven't seen any Windows for years. So I think Ford was the last car maker who used Windows for its infotainment system, and that must have been 5 years back when they ditched it in favor of QNX, by the way, and Qt. And Windows costs a lot of money, so we don't want that. So should you use custom desktop or containerized Linux? Well, typically your choice is custom Linux. You build it with Yocto or maybe with Buildroot, but Yocto is the more common one. You have a pretty steep learning curve, so it takes you probably some weeks to really understand what you're doing. But you have a couple of good books available and also a couple of good consultancies helping you out there. The good thing about custom Linux or Linux in general is you have thousands of ready-made packages. And you have all the device drivers. You have packages for over-the-air updates, for VNC client servers, for machine and cloud communication, for deep learning, and whatever. There's hardly something where you don't find a ready-made package. That's cool. You can adapt the BSB to your needs. You can remove packages, you can add packages, you can add your own packages. So that's good. Desktop Linux, well, it just has a bad user experience. It's the problem with X11, for example. You have to customize, you have to cripple a window manager, and you won't be able to do that. It's pretty reluctant. Containerized Linux. So that is an interesting concept, interesting idea. And the main contender here is Horizon OS from Toradex. And the big advantage here is you can start with application development right away. You don't have to build your own Linux distro. So you get a container, and which is your Linux system. And if you need some package, well, you just add it to the container. It's just a sudo apt-get install, and it's there. So that saves you a lot of time. You can write your applications right away. It's pretty easy to update. You can pull containers from repositories, and you can even update your host Linux system with something like OS3. And that means OS3 actually also allows you to update your bootloader over the air, which is a pretty cool feature. So with Mender, for example, you would pay for that feature. It's not in the free Mender edition. The problem may be that you have to do your own package dependency management if you have too many containers. If you have, say, something like less than 5 containers for some application and services, you're probably fine. Especially if you have a single application system, then you should really look into Horizon. It may be a good idea, and it saves you a lot of time. I haven't used it in production, in products yet. I have tried it out, so makes a lot of sense to me. Has its pros, has its cons, like every other solution. So, but check it out. Now that we have a clear picture of software architecture, we move over to hardware architecture, because the nicest software architecture doesn't help us if it's not supported by a good hardware architecture. So the first thing I'll look into is, how do we design systems with multiple displays? The traditional way is shown here in the photo. You see 3 terminals, so that is 3 display computers. So it's a box with a display and the processor inside. That's a terminal or display computer. Well, it might not be the best idea. So look at this diagram here. You have 4 terminals, and each of these 4 terminals has socks. So they may have different socks, 4 different socks. You may have 4 different operating systems. You may have different window managers. You may have to use different GUI and application frameworks to implement your applications on these 4 terminals. They may come from different companies, or at least from different teams. Typically, they come from different companies. Each of the terminals is connected to LAN and to CAN, so it's a lot of cabling. So it's pretty obvious that you have lots of duplicate hardware and software, which results in high material and development costs. You basically develop the things 4 times here. The advantage is you do not need to do any PCB modifications, which you need to do in the other approach. So my favorite approach, or how I would build a terminal these days, is shown here. So I have one system with 4 displays connected. So the system is something like, it's often called a box PC or so, and it's connected with multiple displays. So you turn we have just turned the 4 terminals into 4 apps. So we have turned hardware into software, which is a lot cheaper. Software is easier to change, easier to update, and so on. So that is a huge advantage. Then, obviously, you have a single SOC, a single operating system, a single window manager, and you use the same GUI and application framework, hopefully Qt, for development. It's connected to one LAN and one CAN, and that's important. So you can take the idea of merging a lot of hardware into one system. You can take that a lot further. And a car, for example, typically sports something like 80 ECUs. A Tesla only sports 12 ECUs. So they have moved most of the ECUs into their, what I call a super ECU. That is this single system. And well, it saves them a lot of money, and it makes things like a system update very easy. You do not have to update 80 different computers in your car. You update one computer, your super ECU, and that's it. And the other 10 or 12 ECUs in there, most of them, I guess, don't need an update. And suddenly it's the user, the driver, who can do the update, and you don't have to take your car into a garage and pay professionals a lot of money to do an update, like for your maps, for your navigation app. So BMW charges you 120 euros for that. So the super ECU, the advantages are definitely you have no duplicate hardware and software, you have low material and development costs. We talked about the system update, and it has one other nice advantage. It saves on chips, so you mitigate the current chip shortage. You don't have 4 chips of each. you have just one, or even if you integrate ECUs, you instead of 50 chips for one thing, you have one chip or two chips. So that is a huge advantage, and I think we have to live with a chip shortage for some time. The downside is you have to do some PCB modifications. You cannot, and we'll see that in a minute, you cannot simply adapt HDMI or plug in HDMI cables here and connect your system with the displays. They would just fall out. And so you have to use some special connectors and some special cables here to do that. So that is the little downside you have. But that may go away soon. I think in 3 to 5 years, that's just standard. Operating conditions have a very strong influence on hardware selection. So just look at that. So electronics work only in a specific temperature range. For harvesters, it's -40 to +85 degrees. They must work in the summer, and some must also work, say, in winter to pick up the sugar beets and load them on a truck. That happens in December or January. That may be in Siberia, and then you have really cold temperatures. Light. You do not want to have this catastrophe here. So this is actually the rear view video, and the evening sun was shining directly on the display. Well, I didn't see much when I wanted to back out of a parking spot. I saw a reflection of my wife on the passenger seat. So, but that's not what you want. Your display needs to have high contrast, high brightness, and obviously some anti-reflection measures. Dust and water. Your terminal must be protected against ingress of dust and water. So what you need here is typically an ingress protection rating of at least 53. The 5 means it's dust protected. The 3 means it withstands water spills. So it will withstand the inevitable coffee and Coke spill. That's it. You can take that further. So you can take that to 69. So when it's really dust tight and airtight and watertight, but then you will run into thermal problems because the processor will overheat. So you always have trade-offs. One operating condition which is often overlooked is vibration. You are sitting on a 1,000 horsepower harvester, and you're racing over a field, so it's off-road, obviously. So what the standard Ethernet or serial connectors, so RJ45 and D-sub9 connectors, they would just fall out after a couple of days. That's how much vibration you have. So what you use are M12 connectors, that's the green cable here, which you screw tight into the connector, or you use Deutsch connectors, which you plug into the socket here, and then they snap in. And if you try to pull them out, it will be painful for your fingers. So they are extremely hard to pull out or unscrew again. Now we come to the finale grande. So what we wanted to do, or one important purpose of our system architecture is the selection of a SoC, of a system on chip. And how do we do that? So what we do is typically or what I did here is I list the most important requirements for SoC selection. And I actually show these for 2016, what was fashionable there and what I would use in 2021. The black requirements are just would give you a run-of-the-mill, rock-solid but boring ECU or super ECU. Remember, we want to build a super ECU, not these terminals, these standard terminals. We want to build something special, which will give us a competitive advantage for the next 5 to 10 years. What is important is they should have a lifetime of 10 to 15 years. So your SOC should be supported for another 10 to 15 years, which is typically the lifetime of your harvester or of your machines. Now, the red requirements are the interesting things. So I would say we want an MCU. Well, we can use the microcontroller for real-time or safety-critical functionality. It's much easier to certify than on a Linux system. Or we just want to offload some processing, like the CAN processing on the microcontroller. Always good. Or we want to merge some ECU functionality. We want to run that on the microcontroller. We want the SOC to be able to drive at least 2 external displays, if not even 4. Ethernet should provide a bandwidth of 1 gigabit per second. You have typically 3 to 5 cameras, video cameras on your harvester. You must display the video streams, or the video streams go into a neural engine to do some image recognition. For example, you can determine the ripeness of maize by looking at the color. The yellower maize is, the riper it is, and the greener, the less riper it is. And ripe means, I think, you use you cut it shorter, and not ripe means you cut it longer. And the cows will thank you for that. Because they will deliver more milk. It's not a joke. So now let's select a computer module or a SOC. You see in the upper table on the horizontal axis, you see the requirements again. And on the vertical axis, you see some modules here from Toradex. It's Toradex because they have nice tables like that, and they also give prices, which is very rare in the business, and they actually deliver really high quality products. So the first 2 modules here are or represent the past, what has been used in the past. The IMX 7 is, well, it doesn't even have a GPU. You will find it in some low-end terminals. Maybe a good choice for them, but it's rare. You find them rarely. The IMX 6 is so far at the moment still the bread and butter SOC. And you see, yeah, it satisfies our requirements pretty nicely. No Wi-Fi or Bluetooth. You could modify your PCB and connect a Wi-Fi and Bluetooth module via UART, and then you also have Wi-Fi and Bluetooth. So you could turn that into yes. The lifetime is a bit short, just 7 years left. It's still a good SOC. Then come the SOCs which I would think are good for our super ECU, for what we have in mind. You have the IMX 8 Max, which is here the absolutely top-end SOC. And you see that. So 6 application processors, 2 GPUs, one doubles up as a neural engine. It drives 4 displays. So that sounds very much like what we want. It has 9 years left of life, so that might be a bit short. The IMX 8 Mini, well, it has one drawback. It only drives 1 display, and it doesn't have a neural engine. Might be a good choice. The IMX 8 M Plus, that is again, that's a perfect choice. So that fulfills all our requirements. So that could be the one we choose. So now it's high time to look at the prices, at the costs. and we look at 500 units, and we see, well, the max is pretty expensive with 230 something euros. The plus clocks in at 130. And so now you will start thinking, okay, do I really need the super compute power of the max? Or am I happy with what the plus delivers? Or maybe could I even do with the mini? And you will look at your requirements again and prioritize them newly and look at it from different angles maybe and come to a different conclusion. But for us, yes, it's the plus. That is a very good SOC for our super ECU. You have two choices when it comes to your super ECU. You can buy an off-the-shelf terminal. The problem with both approaches, the one with built-in display or the box PC without a display, is, well, there are hardly any IMX8s available at the moment, very rare and not the right ones. I didn't find a Plus, for example, neither did I find a Max. They do not support a second display, and here with the box PC, the connectors are not vibration resistant. And the big problem with off-the-shelf terminals is the terminal chooses the SOC and the connectors for you. It is not you who chooses that. And that brings us to custom-made terminals. And custom-made terminals are two options. You can assemble a box PC or terminal from its main parts, and that's actually shown on the right-hand side. So, and you have companies like here, Bopla, for example, who do that for you. So you tell them, okay, that's the SOC you want to use. That is the PCB for the touch display. You want a certain IP rating and so on. And then they put that together, assemble it, and charge a little bit, and you're fine. The other option, if you need some extras, well, you need to modify the PCB. So if you want 3 instead of 2 cans, for example, you need to modify your PCB. If you want Wi-Fi or Bluetooth, you often have to do a modification, or if you need an RFID card reader, that means typically PCB modifications. You can hire companies for that. Maybe you have that knowledge, that expertise in-house. It depends. So my favorite option is probably this, but you might have, for the external displays, you might have to do a little PCB modification. So you will end up with something in between. And this is how my super ECU or super terminal would look in 2021 if I would be able to design it as I wanted. But normally customers have their own ideas, and there are limitations with, say, other companies who provide the ECUs. They might not provide all the data you need. So it's an ecosystem with many players and many humans and many other systems, and they all have their own mind. So you might not get what you are envisioning. So now you know what I'd love to design, and I hope you have a good idea of how to build an architecture for a Qt embedded system. I say thank you very much for your attention. You can reach me, you see it by mail, by web, and I have a newsletter where I talk about things like that as well. So thank you very much, and I'm open for your questions.
Thank you so much, Burkhard, for a very thorough analysis of the architecture of these systems. It was very enjoyable. And we hope that our audience will have questions. And let's see if we can open the Q&A chat. and see if we have questions from our audience. Maybe a little shy yet.
Come on, there's, I think, one. How?
Yeah, it will be projected.
Shall I read the?
It will be. They should project it.
Yeah.
Usually, they project it on the main screen. Here we go. How do you suggest to learn how to customize Weston? I tried to use Gen IV, but it looks really overcomplicated. I just wanted to keep a particular application on top of everything else. I resorted to patching Weston itself.
Yeah, that sounds like it is. So you have a pretty good documentation about Western configuration, and something. Yeah. So what I've done so far is a lot less what I've shown. So I've just one full screen window, and that was pretty simple to configure. And you're trying something more difficult here. To be honest, I haven't done it, so you may want to look into the QML Wayland compositor. It might be easier, especially if you know, and I guess you know, Qt and QML. That might be the easier choice to get. Or you find a customer, one a car maker or so, who gives you the time to speed up. So sorry, I can't give you a solution here right away. I would have to try it out myself.
Yeah, that's an honest answer.
Well, it's I've seen demos from the Geneva Layer Manager. And yeah, looks like what I presented there, that you could do that, but I don't really know how to do that.
Okay.
I'm probably will try out these things. So eat my own dog food. So I'm talking here and how you can do it, and now I need to try out some things. So yeah.
Okay, let's see if we have another question. Which market and technology trends shape the architecture at the moment?
Yeah, we have mentioned we have mentioned one market trend. It's actually a negative trend here: chip shortage. So you must be very aware of the chip shortage. That means, for example, I was on a project earlier this year. And we had to buy the SOX, the IMX8M minis, in January already. So Toradex had to buy them or order them from NXP in January, and you couldn't wait any longer. And my customer waited for some other chips, for some microcontrollers. They waited until end of April. And then they had problems to find enough of them, and they paid a much higher price. With technology trends, it's probably, well, you will see a lot of inferencing on deep neural networks. So you'll see image recognition. So I mentioned the example with the detecting the ripeness of maize, the color of maize directly. That would be a classical image recognition problem. There are companies, so Class, another harvester maker, has started that for grain, so for wheat, for example, and figure out whether they have to clean it more or less, so whether there are some dirt particles in there and how many. So they can do that with image recognition. So there's a lot going on there. And so you have to take care that you can do things like that, say, in 5 years. So the bigger companies have started that. And the smaller ones, the niche players, well, they just don't have at the moment the money, neither the resources for that.
Okay.
Yeah. Okay.
No,
Let's
go ahead.
do it.
It looks like we have another question.
Good.
Modern systems tend to be more and more distributed between the embedded device and edge cloud environments. How does Qt support such type of distributed architecture where applications may potentially live across different environments?
Aha, that's from my friend Roberto.
Ah.
Wind River or ex-Wind River. I don't know whether you are still there, Roberto. Good to meet you again. Yeah, that's actually a thing. You saw probably the rectangle, the blue rectangle with cloud in my diagram. So, but unfortunately, I had to leave that out because of time constraints. It was already pretty long. And with Qt, it's actually pretty, it's well supported. So you have the, for example, the Qt MQTT module, and you also and you can send, say, machine data. You pack it into a MQTT packet and send it to the cloud, say to an AWS or Azure cloud, and they all understand MQTT. You just have to define your messages, what your message means, what the bytes mean in the message, but then you can just use these two Qt packages, this Qt package, and send MQTT packets there. So it's basically a client which sends data to a server. And the MQTT package is actually under a marketplace license. So for, I think, $130 per year per product. So that's pretty affordable by now. Or if you want to use, say, co-op, same story. There's a Qt co-op module under the Qt marketplace license, and you could use that as well. That's the other option. Or you can use web services. You have the Qt web service module, if that's your thing, or the Qt WebSocket module. You could use that. You could just use a HTTP. So that is all possible. And you typically have from the hardware side, you need an LTE modem on your terminal, which you typically have on a Harvester these days. And yeah, or you can use the user's smartphone for the cloud connection. So then you move the costs from yourself to the user. That's also done.
All right. Okay, what do you think about the use or abuse of Docker in embedded systems? It could be said that it's just a fashion of the moment, unjustified when using a build system like Yocto project. So this audience member has a strong feeling about this.
No, he actually has a consultancy business and providing Yocto services.
Okay.
And yeah, I fully understand the question, and I'm not at the moment. I'm not quite sure whether containerization, so using Docker containers, is the right thing to do. So I would love to do a product with that and see how that turns out. So I think it's if you have, say, a single application, it might be a good way to do it. If you have multiple applications, say a couple of services as well, and all put them into a container, I'm not so sure how performant your system will turn out. And you need a Yocto build anyway. So that's the funny thing. You need to your base system is built with Yocto anyway. So there it comes in. It's a pretty simple system. So, but still you need it. And so, yeah, it may be a fashion. Well, Toradex is betting heavily on that, and they are spending good money on it. So it's a thing to watch. And it may be the right thing for some systems, but not for all. If you have the expertise about Yocto in a project, or you can buy it from you, for example, then I would say, well, if you have that expertise in your project, go for Yocto. So that's what I would do. So, and it's not, well, you struggle a little bit to get your first application, a container working on your system. So it's a bit, it also has its problems. I hope I answered your question. And we'll see whether it's abuse or good use in the next 2-3 years, I think. Good. Next question.
All right. Do you have any hint on how to configure Weston for RDP VNC? Does it require BSP modification at Yocto level, or can the BSP be patched after build?
Oh, I'll answer that question if you pay me.
Fair enough. Fair enough.
That's a deep technical. Do you have any hint?
Yeah.
Configure Weston for VNC. I know someone who could do that. You might. I guess you are from Italy. You might know the company Ispirata with Dario Freddi, and I know that he would be able to do that, or his company would be able to do that. They helped me to getting a VNC server working for a very old SOC where there was no Wayland. So yeah, it's does it require BSP modification at Yocto level? I don't know. You could also ask Marco Cavallini. Probably knows that. Sorry, that's too technical. So I would have to think about it.
It's very technical. Yeah, we have a very demanding audience tonight.
Yeah, that's I mentioned it earlier. So that's the things I will look at now that I. So it was for me. It was first thinking about the architecture. What do I need? And then I will look into these topics like configuring Weston. And so on, and really try that out myself. And then you'll say a blog post probably somewhere. No, where is clear.
All right.
For us.
Okay. What use cases have you encountered for RS-232 ports other than GNSS receivers? 4 seems very high from my experience. 0 for 95% of off-highway machines, 1 for the remaining 5%.
Well, with harvesters, it's you are right. So probably. I had earlier this year. I built an operator terminal for medical cleaning robot, and so one UART was used for an RFID reader, so that people could authenticate with their tag. Another UART was used for hooking up a Bluetooth module, because the terminal communicated via Bluetooth with the robot in the next room. And the third one was used for an LTE modem to communicate with an LTE modem. So now it's 3 already. Was there a fourth? I think there was a fourth one. So forgot that. So on harvesters, I've seen typically 1 SU as well. So for some legacy systems, need an RS-232 port. GPS or GNSS receivers, yeah, that's certainly a good one. Yeah, if they are typically, the socks are. I'm looking on my socks, so they are typically lacking module or GLONASS module. Yeah.
Okay.
But there's a world outside harvesters.
Is there?
Yeah, I sometimes I'm wondering myself. Yeah.
Well, they are fascinating machines. I mean, it's a great application. Yeah. It's a great application.
A lot more fun than building infotainment systems for cars, because you can do a lot more. You're not just doing the umpteenth media player or radio. It's pretty boring. But on a harvester, you can actually, you could, if you do it, you could ruin the engine. You have you have the power to tweak the parameters, to fine tune it, and so on. Not the normal user, but special users or developers. So,
of course,
some co-developers actually made the engine sound pretty broken. And the sweat was running.
Yes. Oh, no.
It wasn't me. Yeah. Oh, yeah.
Okay. Does it look like... Okay. All right. How would you do the communication with the cloud?
Oh,
you did answer a little bit already, but...
Yeah. We answered that, I think.
Yes, I think we have already answered that. You talked about even the smartphone of the user, if you want.
That's actually for park meters on remote parking lots, like for hiking in the mountains here. Well, it's the good old park meters where you feed in coins. And the typical problem is, oh, I'm missing 10 cents. Where do I get 10 cents now? And then now, well, you could put in a modem, but that would be really expensive. And you would have to change the park meter. And what they do is, they just put a number there, so to identify the park meter. And then you have an app on your smartphone, and type in the number, or it even finds via your position, it finds, you're on this parking spot, so, okay, start parking now. And when you come back, you stop parking and pay exactly the right amount of money. And that's a pretty clever way to avoid changing the hardware.
Exactly, yeah. And then they're very easy to use, and the user experience is absolutely good.
And much easier to change than your Qt embedded system.
Absolutely.
or embedded system, it's not, well, it does have an LCD display, and that's it, and some buttons. That's a park meter.
Yeah, that's what you need.
Good.
Okay.
There are two more questions.
All right. So, is it good to use the SQLite database in embedded Linux? This is a more generic question.
No, it's a good one. So I'm asking that myself. Well, I actually have used SQLite in many systems. You do not want to use Postgres, for example, or MySQL. They are just too big, and so I haven't seen that. And so your database of choice is SQLite. With all the problems, so they are not thread safe. So if you have multiple applications or multiple threads accessing your SQLite database, you have to do some synchronization on your own, and they are stored in files. It's the thing you have. So if you need a database, say for customer data to do all the accounting on the harvester, how much diesel has the harvester consumed, how much have you harvested, what's the area, and so on. You all need that to do the invoicing. You put it in a database. I try to avoid it, but I can't. And sometimes with the logging, for example, if you log CAN messages, I wouldn't do that in an SQLite database or in an SQL database. That's the wrong database type. You would probably use a time series database for that, because that's exactly what you have. You have a time series of 10 messages, and you save that in there. And they are built exactly for that purpose. So it's in some use cases, that's the way to go, SQLite. I often use Q settings instead, so that may be a workaround. it actually has the synchronization built in. It's a very simple format, the .ini format. So often that's good enough. If you need more, well, it's often, I think it's just people, okay, we need a database. Otherwise, it's not a real it's not a real system. So a serious system needs a database. So often you can get away with Q settings, I would say.
It's like a psychological crutch.
A little bit, yeah. We have one more question.
Yes, let's see. Okay, I'm using remote object to communicate between HMI and business logic. Do you think it's okay for communication between different devices at business logic level, or there could be some drawback?
I wouldn't pull Qt remote objects into the business logic. I would say that is wrong. So the business logic shouldn't know about the communication mechanism. That is exactly where the interface, the port comes in, and where the adapter comes in. So the adapter can provide communication via Qt remote object, and so each of your applications has a Qt remote object adapter to inter-process or inter-application communicate. Business logic is not prepared that, and for that it's perfect. So I think it's by now I would prefer it with DBoss, and I've actually used it, and in a recent project I've used remote object, hidden it away so that I can exchange it, say, for some proprietary TCP protocol, or so if I need that, or for any other protocol I might need. So that's perfect.
Okay, so I think that the time for the questions we can say that it's over now. You can continue the discussion on our Discord channel, which the link was in the chat before, and you can also here is the Discord channel. Yeah. And I just want to remind you about the course that we will have in October, Qt Quick Pro, and that you can register for. If you register before the 31st of August, you will get an early bird special on it. So go and register, and the course will be in Italian language. And you can also contact the QtDay in our on our social media. And we hope you enjoyed this last talk of QtDay, and we will hope to see you in our course in October. We thank Burkhard again for the very interesting talk and for the lively Q&A session. And
thank you a lot. So for the good questions and for the participation. And of course, I hope that Italy will win the Euro.
Of course it will. Thank you. Thank you for your coaching for Italy.
By far the nicest football there, and so I hope. Yeah.
Thank you. We appreciate a German rooting for us.
Obviously, there's some Schadenfreude against the English in there.
No, why did no? I would have never thought that. Okay. Have a nice day, everybody, and till next time. Bye bye.
Thank you very much. Bye bye.